Now today we start with introduction to state space. In this we will cover why there is need for state space representation, and second, advantages of state space techniques. Now why state space representation is essential. In this we will cover history of state space analysis and significance of state space analysis. Now if you see a control engineer, what is the role of control engineer? A role of control engineer is to develop a model, then check stability, and if the system is unstable, then it has to design a controller, and moreover he has to check the performance. Particularly if you want to check the stability, there are various techniques are available. The techniques are Routh-Hurwitz criteria, root locus, Nyquist plot, Bode plot, Nichols chart. So all these techniques are the classical techniques. Then as far as the controller design is concerned, the main controllers which are used in a classical control approach, that is PID controller and lag lead controller. So all these techniques are based on transfer function approach, and that has been developed around say between 1920 to 1950s, and still the research work is going on in these directions. But because of the development of the digital computer, the state space technique has been come, and that is become after 1960s, and these state space techniques are based on time domain approach. But you know that before 1920, that is before the development of the transfer functions, all the methodologies are based on time domain approach. But after 1978, all the state space approaches and classical approaches have been combined, and they form a new approach that is called robust control approaches. Now about the important role of this state space in comparison to the classical approaches. In case of state space, we have to know what are the internal parameters of the systems along with input and output, whereas in case of transfer function approach we don't need, we cannot get any information about the plant, only we are knowing, we are applying input and we are getting the output. Now I will explain this point through an example. Suppose I have some medical problem. What I will do? I will go to doctor, and definitely I will go to doctor which is nearby to my place. Then I will tell my health problem to doctor. Doctor hear my problem, and what will happen? He will prescribe the medicines. Then I will take that particular medicines, and then I will wait for 3 days. If I won't be cured, then what I will do? I will go to same doctor again. Then he will say, no, you have some major problem. Now in that case you have to go to higher center, or in big city you have to go. Whenever I will go to that big city or a higher center, when I will go to that particular doctor who is a specialist, what he will do? He will not prescribe medicine. First of all, what he will do? He will say that you test, you do some testing, particular urine test, blood test, and whatever reports will come, based on this he will prescribe the medicine. So this is nothing but the advanced control approach, or we can say state space approach. Whereas earlier, where we are applying input, getting output, just like a previous doctor, so that is, we can say, classical approach. Now about the advantages of state space techniques over classical techniques. Classical approaches are applicable to only linear, time invariant differential equations, whereas state space approach can be used to represent linear and non-linear systems that have backlash, saturations and dead zone. Now you will find that in case of classical approach, we are using a linear system only. So original system, and we know that practical systems are non-linear, but analysis using classical approach cannot be possible for a non-linear system. Therefore we have to use the linear model. Definitely whatever results will get, that is not exact, that is an approximated result. But at the same time, if you design your controller, testing has been done on the nonlinear model, your analysis will be perfect, results are perfect. So, all these type of analysis, that is particularly linear plant, is possible in classical approach, whereas if the plant is non-linear, it is possible in case of advanced control approach. That is the first advantage of state space over the classical approach. Second, state space approach can handle the system with non-zero initial conditions. Classical approach is based on transfer function approach, and you know that in transfer function we have to neglect the initial conditions. But whereas if you go for a state space approach, we can consider the initial conditions. Third, state space methods work directly with the governing differential equation in the time domain. As I told earlier also, state space approach is basically based on time domain, and classical approach is based on S domain or a frequency domain. The state space approach is applicable to time varying system. You see the aircraft has some fuel, and it is move up, what happens? Fuel decreases, that again the weight decreases, weight of the aircraft decreases. Therefore, whatever technique you will develop, that should be for time varying system. So that time varying concept can be applicable in case of state space, where it is cannot be applicable in case of transfer function approach. Third, state space equation is applicable to single input, single output, as well as multi input, multi output systems. In a practice, most of the systems are multi input, multi output time. Therefore, we should have techniques of stability as well as control design which are applicable for multi input, multi output system. So that type of approaches, particularly stability and control design, are easily available in a state space approach, whereas it is very cumbersome for in case of the classical approach. Last point, state equation are always first order irrespective of the system order input and output. If you see any transfer function, how you define transfer function? Transfer function is Laplace transform of output to Laplace transform of input, initial conditions are 0. So here in transfer function we get different order system, third order, fifth order, 100 order. But if you see the state space equation, that is always a first order equations. Now, whatever point I have discussed, you can also find these points in the following references: Ashish Tiwari, D. Rai Chaudhary, Norman S. Nice, and K. Ogata. So these are the advantage I have explained, that is a general advantage, but there are advantage which are be helpful from practical side, that is from practical point of view, particularly from control design point of view. So that advantages, the conventional indicators of the closed loop performance are the closed loop poles or the location of the closed loop poles. For higher order system, by varying a limited number of constants in the controller transfer function, one can vary the location of only a few of closed loop poles, not all of them. See here, if you want to design a controller, that controller design means final result is based on the closed loop poles. So what my aim is that I can place the poles anywhere in the S planes, and each poles contribute in the performance of the system. So we will find that if you go for the classical approach, the controller design, when we design a controller, we cannot place the poles as per our requirement. So this is a basic disadvantage of the classical approach. So we will see this point through an example. Suppose if you take GS equal to like this, GS equal to say S plus 2 divided by S minus 1, S plus 1, S plus 3. Now this is a transfer function, and you will find that in these transfer functions there are 3 poles and 1 0, and in this case there is one pole on the right side of the S plane. Therefore, this plant GS is unstable. Now we have to design a controller for this plant. So how do you design a controller? So in order to design a controller, what is the best term is here, that is a S minus 1 pole in the denominator, we can cancel it. And the second thing what we can do is that we want that there should not be any steady state error, we can add one integrator. So therefore, we can write a controller C of S equal to, I can add one gain factor k, then this is S minus 1, this need to be cancelled, so I can write in the numerator and divide by S. So this is the controller, GS is a plant and CS is a controller. Now what we want, open loop transfer function with controller, so GS into CS. So we can multiply it. So what will get, S plus 2, S minus 1, S plus 1, S plus 3, and this is multiplied with this controller K, S minus 1 divided by S. So we will find that this S minus 1 and this S minus 1 will cancel, and finally we get as S plus 2 divided by S plus 1, S plus 3, and here is the one gain. So this is the open loop transfer functions. Now what we want, a closed loop transfer functions. How do you write closed loop transfer function? So closed loop transfer function is Ys by Rs equal to Gs into Cs divided by 1 plus Gs into Cs. Now we write down this transfer function as K S plus 2 S plus 1 S plus 3 divided by 1 K S plus 2 S plus 1 S plus 3. Now we solve it, and after solving we will get result as K S plus 2 divided by S plus 1 S plus 3 plus K S plus 2. Now again we simplify it, what will get, K S plus 2 divided by S cube 4 square 3S plus K S plus 2. This is a closed loop transfer function. Now in this case what we will do, we will take the different values of K. Now first of all what we will do, we will take K as K equal to 0.5. So you will get the roots are minus 2.9180, other roots are minus 0.410 plus minus 2236j, and when we take K equals to 10, we will get roots as minus 2.2113, 0.8944 plus minus 2.8714j. So we will find that for K equals to 0.5 we have got these roots, and K equals to 10 we got these roots. So we will find, but what my aim is that I want that my one root should be fixed. Let us say my aim is that my root should be around, let us say at minus 10, and other roots are at somewhere in these locations, say at around minus 7. So this is my requirement. So this type of requirement cannot be satisfied by means of this approach, and therefore whatever the desired performance we required, that cannot be achievable by means of this approach. Therefore this type of disadvantage can be covered by means of a state space approach. In the state space approach we can place pole anywhere in the S plane. Now about the second point, you have a plant GS third order, and what is the controller? Your controller is of first order, so final plant should be of fourth order, but we will get a third order. Then can this thing practically possible? Plant is third order, controller is first order, we got the result we should get as a fourth order, but we are getting a third order. So, but these type of things, although we observed in theory, but practically there is some problems. These type of things cannot be possible in practical sense. Let us say I will draw now the root locus of the plant. Suppose I have taken the same plant, let us say GS equal to S plus 2 divided by S minus 1, S plus 1, S plus 3. This is K. Now we will draw the root locus of this system. So how will you draw the root locus? For root locus, we have to show all poles and zeros. Now the poles are, say here S equals to here pole, then here another pole, L equals to minus 1, here is plus, here S equals to minus 3, and this 0 S equals to minus 2. So this is open loop plant, but afterward what happened, we have designed a controller. For the controller you have a plant like this, GS equals to K S plus 2 divided by S plus 1, S plus 3, that is GS into your CS. So here when we show the poles and zeros, so we have one pole at S equals to 0, another pole at S equals to minus 1, and another pole at S equals to minus 3, and we have zeros at S equals to minus 2. So 3 poles 1 0, and this is for GS, which is an unstable plant. Now our aim is basically for the stability of the system. System is to be stable. Therefore I have taken this plant GS into CS. Now we want to draw the root locus. How will you draw the root locus? I think you might have studied in a classical approach. Root locus starts from pole and terminate to zeros. So you will find that there are 3 poles and 1 zeros. So one pole will terminate to zeros. Then what about the other poles? So these 2 poles will terminate to infinity along the asymptote lines that you might have studied in the root locus in a classical approach. So now here we will draw the root locus of the system. So first of all we see the location of root locus on the real axis. So the real axis we say, so this is the basic locations. When there exist odd number of poles, the root locus will lie. Here is a odd number, but here this is even, so root locus will not lie here, and the root locus lie here, so odd number of poles. Now in this case what will happen, root locus start from pole, terminate, and it will also start from here, here start, it will terminate into 0, but for these 2 cases the root locus will terminate into infinity. For that purpose we have to calculate the centroid. So how will you calculate centroid? Centroid is, that is summation of real part of pole minus summation of real part of zeros divided by number of poles minus number of zeros. N is poles, M is 0. So what we will get in this case, what is the poles? One at minus 1, other at minus 3, so we will get minus 4. This minus, and what is the 0 at minus 2, so we will get minus 2. Then how many poles? 3 poles, 1 0, so we will get 2. So we will get minus 4 plus 2, 2, get minus 4. And what about the angle? Angle defined as phi equals to 2q plus 1, 180 divided by n minus m, and in this case your q varied from 0, 1 up to n minus m minus 1. So when q equals to 0, so phi a will get as q0 will get n minus 1 2 will get 90 degree, and when q equals to 1 will get phi as If you add q, so 180 into 3 divided by 2, so we will get around 270 degree. So here these are asymptotic angles. So root locus start from pole, it will start from here, and there is a breakaway point. So that we calculate by dk by ds. Here I am not calculating. So approximately value will be coming at minus 0.5. So here what will happen? Root locus start from here, it will move this side, and another will this side, and another root locus start from this pole and terminate to 0. This is the location of root locus in the real axis as well as in the imaginary axis. Now what about the stability of this one? You will find that you can vary k from 0 to infinite. This is infinite, this is k equals 0 infinite. System is stable, whatever k will get. But can it possible in a real time? Sometimes it happened that students are working on some project, and in simulations they are getting result. But when the same thing they are implemented in a real time, they are saying that result are not coming, because in simulation we can getting result, but in hardware a real time result are not getting. So if you use the classical approach, this can be a possibility. So here also we will find that in this particular examples, for k varying from 0 to infinity, k by 0 to infinity, your system is stable. But if you take this example in a real time applications, this is not possible, system is unstable. So this type of verification is possible using a state space approach. If you take this problem in the state space, you will find that system become unstable. So whenever I will teach the modeling in a state space and analysis control design, I will take same example and I will show that this plant with controller is unstable. This has happened because we have done a pole zero cancellations. Therefore, particularly when we are doing analysis in a classical approach, we should avoid this pole zero cancellation. If the pole zero cancellation is there, there is a problem. Just as we have seen the problem here. Here the problem is that your order has been reduced. System is stable, but in real time system is unstable. So in the next part, I will explain you how to model a state space approach, then different types of modeling. Now these are some references. Thank you.